Hello and welcome back. Now, the very first project that I did for this YouTube channel was this thing, the current probe. Now, it's been more than a year since then, around 1 year and 3 months. And in this time, I made quite a few videos, and I would just like to take this moment to thank all of you guys for the support you've given me. All your likes or your views mean a lot to me, and that's really the reason why I keep making these videos. So if you're curious about how you can improve on this thing by making it a bit wider, yeah, you can see that it's a bit bigger. If you're curious about what sort of features this thing has, what makes it better than the old design, and in general what a current probe needs to do to become a bit more useful, then keep watching. So what are the problems associated with this circuit? Well, there's quite a few of them, but the ones that I want to tackle today are just a few. So the first thing is that at the moment, by looking at the circuit, you have absolutely no idea if it's on, if it's off, if it's running, if it's broken. You have no idea about what's going on with it. The only thing that gives you any sort of clue is that by connecting it to the oscilloscope, you see a certain signal. But other than that, there's no indication. Now, this is something basic. It's something that you should add into any sort of circuit that you build. And that is an optical indicator to show that it's supplied. Or in other words, a simple LED. Now, that's not something very complicated to do, so that's not the reason why I made this video, of course. The reason why I made it is because I wanted to tackle a more complex problem. And that being that the output signal, as you can see, is not centered around 0, but rather 2.5. And it's not really 2.5. Now, I mentioned in the first video that you can get over this problem by going to your oscilloscope menu and setting a certain offset, if the oscilloscope supports this. I'm not sure if this one knows how to do that. But anyway, that's not the proper way of doing things. There's a good reason for that. The offset that the probe has is not a fixed voltage. It's not 2.5 exactly. It's half of the supply voltage. Now, the supply voltage in this case is the USB connector. USB being supplied at 5 volts, 5 volts divided by 2 is 2.5. So that's where we get the 2.5 volt offset from. But here's the catch. USB 5 volt is not 5.0000 volts. It's actually somewhere between 4.5 and 5.5. So that's a very huge interval. If anything happens to the supply voltage, then your offset will move. You will no longer be able to have a proper measurement. Since if anything happens to the supply voltage, then this will be interpreted as a current by your measurement. So that's not the right way to do it. So the problem that I want to tackle today is how to remove this offset. How to make the circuit output a voltage that is centered around 0. So let's see how we can do this. What are the things that the circuit should be able to do to achieve this performance? So to understand the problems of the first circuit, let's just analyze a bit how the circuit actually worked. So on our left side, we've got our current sensor, so ACS7 something something. There's an entire series of these, depending on which you've got available. You can use that, but all of them basically work the same. Basically, you've got the current input going through it, and then a Hall sensor which turns this information into an output signal. So how is the output signal in reference to the current? Well, the signal can be characterized like this. So the signal is half of the supply voltage of the current sensor IC plus the current going through the IC times some sort of proportion factor. Depending on the model of IC, this can have various values. This is basically the IC's sensitivity. How many millivolts is it outputting for each amp? Okay, so we've got this part, and then I added this bit of amplification. So what does this do? So this thing will output a certain output voltage, which will be the reference voltage, so the voltage coming from this potentiometer. It has some resistors with it, but to keep things simple, I just left it as a potentiometer. From this reference voltage, it subtracts the useful signal coming from the current sensor and then amplifies it by a certain gain. So the ratio of the two resistors. And to this term, it adds the reference voltage coming from a potentiometer to generate an output voltage. Now this seems a bit complicated. What can we simplify this formula down to? So if we consider that our reference voltage is the supply voltage times the potentiometer ratio, which we set to half of the supply voltage, then we can replace these terms with some other terms. So our V reference will become supply voltage divided by 2. Our signal voltage will be the supply voltage divided by 2 plus current times the sensor's constant. Then we multiply this by the ratio of resistors, and we add to it again the reference voltage, which is the supply voltage divided by 2. Now in here, these two terms cancel out, and what we're left with is the supply voltage divided by 2, from which we subtract our amplifier's gain times the current times the constant of our current sensor. And we're left with this thing. And this is where our problem is. The output voltage information contains a constant, another constant, and the current we're trying to measure, and this thing, the supply voltage divided by 2. And as I said, because this supply voltage is not perfectly stable, it's coming from the USB, therefore it can have fluctuations. If we have any sort of fluctuation in this term, we will have a fluctuation in our output voltage. So what we need to do with this circuit is remove this VCC divided by 2. So make some sort of modification that will enable us to contain only this term, the current information and some constants. So how can we do that? So let's go back to our first formula. The first time we replaced our reference voltage by our supply voltage divided by 2. But let's not do that. Let's try something else. So I'm going to replace only our signal voltage with our initial formula, since there's absolutely nothing we can do about this. That's a fixed value, it's done. So what we get is that our output voltage is our reference voltage minus our supply voltage minus the current information times the gain plus the reference voltage again. So it's still not very useful. We still have our reference voltage, we still have our supply voltage. Now let's move the terms around a bit. And we get to something like this. So what I did was I extracted our reference voltage from this term and from this term, meaning that our reference voltage is now our gain plus 1. Then we have our supply voltage times the gain, and we have our current information. And basically, this is the term that we're interested in. This is what we want at the output. We don't want the rest of this. And the fortunate thing is that we can do something about that. And what we want to do is to have all this thing equal to 0. So our objective is to have this entire term equal to 0. If we have that, then the output will only be our current information. And if our current is a negative value, so we've got a negative current going through our sensor, negative times negative will be positive. And our circuit will output only a positive voltage proportional to our input current. So how can we get this term equal to 0? So by replacing our reference voltage by this term, so the supply voltage times our potentiometer ratio, we can rewrite our output voltage in this final form. What you can see here now is that the output voltage is equal to the supply voltage times a term consisting only of constants and our useful signal. So if we can get this term to be equal to 0, so we set the constant so that this is equal to 0, then our supply voltage no longer matters. Our output voltage will then be only equal to our current information. Basically, this is what needs to be done. So the voltage given by this set of resistors needs to be set so that our output signal only contains our input current information. So let's see how this thing can be implemented in a schematic. But there's one more thing to remember. If we're looking at positive currents, so this term is equal to a negative value, then our op amp will not be able to supply that value, since our op amp is supplied at 0 volts. So even though this is a rail-to-rail op amp, it will not be able to output a voltage lower than 0. So at the moment, this circuit, by setting the correct reference voltage, will be able to measure only negative currents, reference to 0, but not positive currents. So that's another thing that needs to be considered. So let's look at the final schematic, see exactly how this thing works out. So this is what I came up with. First of all, I changed the IC, so I'm no longer using the ACS 714. I've managed to get my hands on the 712, the 5 amp version of it. This is a bit more sensitive, so it gives out 180 millivolts per amp. Now regarding the specific IC, just like my viewers pointed out, Allegro makes a ton of these. So if you go to their website, you will see that they make dozens of them, each having their own specific advantages. Now you have some that go up to 1 megahertz, you have bidirectional ones, unidirectional ones, 5 volt supply, 3.3, you name it, they probably got it. So depending on which of these ICs you can get your hands on, you should use that one. I just took this one since this was available to me. Now moving on, what I'm trying to get is a signal, an output signal that's 1 volt equal to 1 amp. That means that my gain will need to be 5.55. So to get this gain, I'm feeding my signal through a 4.7 kilo ohm resistor into my op amp, and the feedback resistor needs to be around 26 kilo ohms to get the said gain ratio. Now for my reference voltage, I'm using a pair of resistors and a potentiometer, and using the formula that I've previously shown, I will need a potentiometer ratio of 0.42. Or in other words, my reference voltage for a supply voltage of 5 volts needs to be around 2.1 volts. So I'm achieving that with this thing, using my potentiometer to calibrate this circuit. Now there's one more thing you may notice. My current sensor IC, LED, very important, I added this LED. Resistor divider, everything is applied from the 5 volts coming from the connector. But the op amp is not. So I switched out the old op amp to the LM741. I had this thing lying around and decided to make use of it. But to be able to use this, I'm using a differential supply, plus minus 6 volts. Why 6, not 5? Well, this op amp has certain input and output voltage limitations of around 1-2 volts. So to counteract that and to be able to use the entire voltage range, I increased the supply voltage a bit. Now where am I getting this voltage from? Well, it's from this thing. This is the differential power supply that I've shown in one of my old videos. So I don't want to go into too much detail on this, go check that video out, there's a link to it in the description. But basically, this thing is quite a simple circuit that will take my 5 volts from the USB and provide me with differential 6 volts, which I'm only using to supply the op amp. And basically, this circuit should now take my current information, center it around 0, and then output it at a rate of 1 volt corresponding to 1 amp of current. So let's see if this thing actually works. Let's see how this thing behaves. So basically this is the board. Now some of the things that I've changed from last time are that I've put both connectors on the same side. So as you can see, current measurement is done on the left side, cables come to the right side. This is just to make it a bit more easy to use. Now on this side of the board I've got the all important LED, and then I've also have my operational amplifier, so signal processing, and then on the other side I've got my current measurement IC, but also the switching power supply, so the differential power supply. Now I've chosen this arrangement, so you can see that on the other side of the power supply there's nothing, also on the other side of the amplifier there's nothing, so only ground. So I did this to keep the noisy power supply away from the sensitive analog part. Hopefully this will work well. So let's try it out, see how this actually works. So I created this setup to test out the circuit a bit. So what I got here is a circuit supplied from the oscilloscope. The output signal is going into the first channel, so the yellow one. Then I've got a power supply on the left side which will give me a certain current, which is supplied through this 1 ohm resistor, which I'm also measuring on my second channel just to give me a current readout. So 1 volt on the 1 ohm resistor will mean that there's a 1 amp current going through it. And at the same time we should get also 1 volt from the probe. So let's see if this thing actually works. So right now we can see that both my oscilloscope probe and the current probe are centered around 0 volts. So now if we add a bit of current, we see that both of them are rising at the same time. So let's just change a bit the scale. So we can see that, although not perfectly, both of them are rising when the current increases. Now if we change the direction of the current, so I supply the resistor in reverse, I get the same effect the other way. So I'm getting a negative current. Both my probe and my current probe are picking this up. So this way we prove that the current probe works in both positive and negative currents, both times centered around 0. So let's see a bit the voltages inside the probe. How is this thing working? Since we talked so much about the reference voltage and the input voltage and the output voltage, let's just see these voltages in the actual circuit. So now if I look at my output voltage, it's around 0.05, so it's not perfectly centered. This probe still needs some calibration, but that's close enough. I can see my USB voltage, the 5 volts is around 4.8, so this isn't 5, and the signal coming from the current probe is centered around 2.35 volts, so it's not centered around 2.5. And my reference voltage, therefore, after calibrating it a bit, is at around 1.95. Now, what I'm noticing right now is that it's not a very stable voltage. Once I connect the multimeter probes to the circuit, the reference voltage moves. You can see that on the oscilloscope. So this circuit still needs a bit of work, or maybe a bit of shielding, but it's good enough. Now, while trying to debug this issue, I found another one. Pretty interesting. Now, this is a Hall sensor, and the principle on which it works is that current going through the wiring is creating a magnetic field, and the sensor is picking up that magnetic field and amplifying that. Now, this is a coreless Hall sensor, meaning that there's no ferromagnetic material or core that concentrates the field from the sensing wire onto the sensor. There's just epoxy between the two. That means that any sort of magnetic field, like one coming from this permanent magnet, will have an influence on the sensor. So right now, I'm not touching anything, I'm just bringing this magnet close up. And you can see that it's already sensing something. Depending on the strength of the field and its direction, it will sense an imaginary current that is either positive, or negative, or positive. And this magnet, being quite strong, can create quite intense fields. So we can see that the sensor can go to a maximum of about 5, almost 6 amps, and the minimum of -4. So this limitation is coming from the op-amp. But nevertheless, this is something that needs to be taken into account when using this sort of sensor. You need to make some sort of magnetic shield, or else you will have all sorts of interference, coming either from external magnetic fields or even from the wiring that is passing the current. All of these can have an influence on the measurement, since the sensor is not properly shielded. Okay, so let's move on to some good news. Let's see how this thing can measure an alternating field, since in the meantime, since my last video, I've managed to build a power amplifier. Let's see how that works out. So this is the new setup. What I've changed is that I'm no longer supplying the current probe from the DC power supply, but rather from a signal generator passed through this power amplifier. And this is one of the projects I've been working on for some time. It's almost ready, it works, but it still needs a front panel. But it does have the all-important LED. So I'm still passing the voltage coming from the amplifier through the 1 ohm resistor, and what I've got here on the oscilloscope in blue is the voltage monitored by the amplifier itself. So this is monitoring its output voltage. Therefore, if we've got 1 volt going through 1 ohm, then it should be 1 amp. So now we can see what the 1 kHz sine wave looks like through our current probe. At the moment, it's around 400 milliamps peak to peak, but we can improve on this a bit. So we can make it bigger. The amplifier can handle about 1 amp of current. Now, one of the things you will notice is that the signal Now, after a bit of a cool down, my oscilloscope seems to have recovered. Hopefully, I'm gonna be gentle with it, also with the amplifier. The amplifier didn't do anything wrong. You're a good amplifier. And we can finally make our measurement. So at 1 kHz, if we overlap these two signals, we can see that there's quite a good correspondence. So we're sensing the signal as it is. Now, of course, there can be some minor adjustments made, but that is from the gain setting, so this can be still calibrated. So let's see what happens if we increase the frequency. So at 5 kHz, still we have a good correspondence. But as we go to higher frequencies, right now we're at 20 kHz, we're starting to see that the sensor is giving a smaller output. And if we go to an even bigger frequency, 50 kHz, it's even worse. And not just that we're not sensing the full signal, but we're also seeing a phase delay between the two signals. So with increasing frequency, the sensor is starting to fall behind. Now there's two components to this problem. First of all, the Hall sensor itself, and secondly, the amplifier circuit, which has a certain limited bandwidth. But both of these can be improved on by using components that have higher bandwidths. So all in all, this is what I wanted to talk to you about. This is the newer version of the Hall sensor. I may be making a third year special after 4 years in which I try to improve on this a bit more. But anyway, let me know what you think about this. Hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and hope to see you next time. Bye bye.